Hello guys, welcome to my YouTube channel. Today we are going to discuss about the forward biasing. Previously we looked at the formation of the p-n junction, and today we are going to look at the forward biasing of a p-n junction. We say that when a p-n junction is formed, the positive ions are concentrated on near the junction. Positive ions are on the n-type and the negative ions are on the p-type. Now we are going to look at this is at no bias condition. When at no bias condition, we realize that the potential barrier is larger, is from this point here up to here. Now I've labeled it as WD. This is the potential barrier with no biased condition. Now, when you apply a voltage in such a direction that it cancels the potential barrier, that is the forward biasing of the p-n junction. Now, what do we do in a forward biasing of p-n junction? We connect the p-type semiconductor to the positive terminal of the battery. We connect the p-type of the p-n junction to the positive terminal of the battery and the negative terminal of the battery to the n-type of the p-n junction. Like that. Now, if you connect a battery, the positive terminal of the battery to the p-type of a semiconductor and the negative terminal of the battery to the n-type semiconductor, the positive terminal of the battery will repel the positive holes in the n-type semiconductor, the p-type. Now, the potential barrier also in the negative terminal of the battery repels the ions, the negative electrons in the p-n junction. These electrons will repel away, and also the holes will repel away, making this potential barrier smaller. Now, these ions, positive ions, will combine with the negative ions, forming positive ions. Now, the potential barrier shifts from this position to this position. This is the new potential barrier. It reduces. Also, in this negative terminal of the battery, it repels the negative electrons to combine with these holes in the n-type junction. Now, the potential barrier also shifts from this position to a new position here. Now that the new potential barrier also shifts to here. Now the new potential barrier becomes WD prime. You notice that with when let's say VD, we notice that when VD is equals to 0, then the potential barrier is WD. Then this also equals to WD. But when VD is greater than 0, our new potential barrier is WD prime. Our new potential barrier is WD prime. Now, also, in this p-n junction, we said previously that when the positive ions are on the negative ions are on the p side, and also positive ions are on the negative side of the junction, there is current. We have the diffusion current. I've labeled it as I majority. We have the diffusion current previously without the VD voltage. Also, we had the saturation current, the current due to the minority charge carriers. That is IS. When you have this, now that we say that the total current due to the p-n junction will be the summation, the total current will be the summation of I majority plus I saturation. I saturation is due to the current in the minority charge carriers. What do we note in the p-n junction? We note that when a p-n junction When a VD is applied to the PN junction, we note that the potential barrier is reduced due to the forward biasing of the PN junction. The potential barrier reduces. We also note that the junction offers a low resistance to the forward resistance. We note that the junction offers low resistance. It offers low resistance because we have forward biased the PN junction. Now, in our next lecture, we are going to look at the semiconductor diode. And semiconductor diode, we're going to look at the semiconductor diode. In a semiconductor diode, we are going to look at the rectification properties of the semiconductor diode. We are going to look at the half wave rectification. We're also going to look at the full wave rectification. Thank you so very much. In our next lecture, we are going to discuss the following.